Move this note down into the corner. Now I want to add a general view to my drawing. I'm going to create an assembly drawing that will use balloons to reference the parts in the assembly to the bill of materials. The first step is to click on the Table tab, then select the table icon, click on Quick Tables, and choose BOM Description Down. Now you're going to be prompted on where you want to place it. I'm going to place it in this bottom right hand corner. Now I'm going to make the corresponding balloons, and there are a few different ways to do this. One way is by clicking on Create Balloons and selecting Create Balloons All. This will create balloons only on the main view that the projections stem from. You can move the positions of balloons by first highlighting them and then clicking on the white boxes. And also notice that when one balloon is highlighted, it is also highlighted in the bill of materials, and vice versa. To clear balloons, click on the Balloons tab and select Clear Region, and then choose Yes. You can also create balloons based on a view. To do this, click on Create Balloons and select Create Balloons by View. Then click on the view you want to create the balloons on. I'm going to choose this projection. And again, to get rid of the balloons, I'm going to click on the Balloons tab and click Clear Region and choose Yes. Now lastly, I will create balloons by component. So first I'm going to click on Create Balloons. Now I'm going to say Create Balloons by Component. And now you can select one or more items. So I'm just going to first select this plow, then click down on the scroll wheel, and notice that the balloon was created. Now I'm going to do this again, and I'm going to do multiple items. Now I'm going to create the balloons by component one more time, but this time I'm going to select the references on the model tree. And now press the scroll wheel, and all the balloons are created. Now I want to clean up the way the balloons look, so first I'm going to highlight all of the balloons by clicking on them and holding Control. And then I'm going to click Clean Up Balloons. Now I'm going to change the offset from View Outline from 0.8 to 1. And I'm going to check the box where it says Create Corresponding Snap Lines, because I find it makes fixing the balloons easier. And now you can preview what it's going to look like. And I'm going to press OK. Clean Up Balloons does a nice job, but it isn't perfect. Notice how balloon number 11 is going across the entire assembly to this bottom line. I'm just going to highlight it and then move it so that it's on the top line. Another thing to keep in mind when making balloons is that you shouldn't have any of the leaders cross each other. It's typically just bad convention to do so, so try and avoid it. And now I'm just going to get rid of these construction lines. Press delete, and there you have our
An auxiliary view is a type of projection view that is projected at a right angle from a selected surface or normal to a selected axis. To create an auxiliary view that is projected from this view so that this circular surface and its pattern of 6 holes are displayed parallel to the drawing sheet, click Auxiliary from the Model Views group. If the selected direction reference is an edge, surface, or datum plane, then the view is projected at a right angle to the reference. This means this edge can be selected as the direction reference for this view. Then click to place the view. Another way to get the same view is to click Auxiliary and select this axis as the direction reference. If an axis is used as the direction reference, the view is projected normal to the axis. If we edit the properties of this view, we can see that the view type is auxiliary. The parent view is named General View, and the projection reference is a datum axis. Also notice that the projection arrows option is set to none. Change this to single, and click Apply to see a single projection arrow added to the drawing. Change the option to double, and click OK to add a double arrow projection arrow. Creating and configuring auxiliary drawing views is easy in Creo Parametric. Datum planes are 2D reference geometry. They have no mass and are infinite in size. In Creo Parametric, datum planes are typically used as construction geometry for features or as a reference when assembling components. The right, top, and front datum planes included in all the default template models are known as default datum planes. Every feature in a model is directly or indirectly created with reference to these three datum planes. When creating datum planes, you can select almost any combination of geometry that defines the plane in 3D space. To create a datum plane offset from a selected surface, you can start the Plane tool and then select the surface the plane is to be offset from. Alternatively, you can select the surface and then start the Plane tool. You can then use the drag handle to offset the plane in a specific direction and distance from the selected surface. The display of datum name tags can be toggled on or off from the Show group in the View tab. While offset is the default datum type created from a selected surface, you can also create planes that are parallel, normal, or through selected surfaces. While a datum plane is infinite in size, you can adjust how much of it is displayed. To change the display size of a datum plane, select the Display tab from the Datum Plane dialog box and enable Adjust Outline. Here, you can adjust the size of your datum plane using width and height values, or you can select Reference from the drop-down menu and size your datum based on a selected reference, such as this surface. Notice how the datum plane size adjusts accordingly. You can always go back and adjust the size by entering values directly. Datum planes can be created using multiple references by pressing the Control key when selecting references. For example, you can create a datum plane through an edge and through a cylinder. By default, the plane is created through the edge and through the center of the cylinder, but you can change this to be tangent to the cylindrical surface if necessary. You can also create datum planes that go through selected edges or axes and are then offset at an angle from a selected surface. The angle can be controlled by a dimension, or it can be set to be parallel or normal to the selected surface. You can use a nearly infinite combination of geometry and options to create any datum plane you need to use as reference in your part or assembly. You'll be glad to know that if you need to place a flexible component into an assembly, it's not much different than placing a non-flexible one. There are just 2 additional steps in the process. As you can see, if you try placing a part into an assembly that contains a flexible definition, such as this flex contact, you're prompted to confirm whether you want to use the part's flexible definition. You could say no and not use the flexible definition, but in this case, we'll click yes and use the part's flexible definition. The next step is to enter new values for the items that need to be flexible. The flexible definition of this contact has an angle dimension that's flexible. In the free state of the part, the angle dimension is 60, but perhaps you'd like that dimension changed to 90 when it's placed in the assembly. Notice that besides entering values, you could also set the dimension value to be equal to a measurement, such as curve length, distance, angle, area, or diameter. In the Features tab, you'll see that a group of features named Test Pad has been added to the flexible definition of the component. By default, features added to the definition are resumed, but can be set to be suppressed if need be. You can use this to turn the display of features in your flexible component on or off. Next, confirm that the entire group of features will be suppressed, and then begin placing the component into the assembly as you would any other non-flexible component. You can see that the flexible part looks pretty different than the non-flexible part. If you cut a cross-section through this assembly, you'll also see that it fits into the connector perfectly. If a change is made to the free state of the connector, the flexible version updates accordingly. Placing a flexible component into an assembly enables you to use the component in an assembled state while also maintaining the pre-assembled state of the model. In Creo Parametric, the shape of every revolved feature is based on a two-dimensional sketch and an axis of revolution. To create a revolve feature, you can either start the Revolve tool and then select the sketch you wish to revolve, or select the sketch first and then start the Revolve tool. If your sketch already contains an axis of revolution, it will be automatically revolved about that axis. If it doesn't, like the situation we have here, Creo Parametric will prompt you to select an existing edge or axis for the sketch to be revolved about. As soon as you select an axis of revolution, the sketch will be revolved around it. The axis of revolution can also be added to your sketch. To do this, just add a geometry type centerline in your sketch. This can be done using the Geometry Centerline tool found in the Datum group of the Sketch tab, or you can convert a sketch centerline to a geometry type centerline using the pop-up menu. Now if you start the Revolve tool, the sketch will be automatically revolved about the geometry centerline you added. To revolve about another axis, you can select Axis of Revolution in the dashboard, or right-click and select Axis of Revolution from the pop-up menu, and then select the axis you're going to revolve the sketch about. To return to using the sketched axis of revolution, select Internal Centerline from the Placement tab. From simple to complex cross-sections, Creo Parametric provides you with several options for revolving sketches around an axis to quickly create solid features. Selected surfaces can be used to create an offset sheet metal wall in Creo Parametric. An offset wall is created by selecting an existing surface and then specifying offset distance and thickness of the wall. To create an offset sheet metal wall, start the Offset tool from the Editing group and then select the surface to be offset. Edit the offset distance and then the thickness of the sheet metal material. In the Options tab, notice that the sheet metal offset wall utilizes the same offset function used in core part mode. This means that the offset can be defined using the normal to surface, automatic fit, or controlled fit methods. To add a bend to this sharp edge, enable the Add Bends on Sharp Edges checkbox and edit the bend radius, which we'll set to be 35. The Offset Wall tool makes creating sheet metal walls to fit in or around existing designs as quick and simple as selecting a reference surface. In Creo Parametric, several types of measurements can be taken from your models. You can use these measurements to better understand the size and shape of your design. To find out what units a model was created in, and thus what units your measurement results will be displayed in, click File, Prepare, Model Properties. In the Materials section of the Model Properties dialog box, we can see that this model uses a unit system of millimeter, kilogram, and seconds. It's important to know what units will be used when evaluating the results of measurements that you'll be taking. The Measure group of the Analysis tab is where you can find a set of commonly used measuring tools: distance, length, angle, diameter, radius, area, and volume. To measure the diameter of a cylindrical surface, start the Diameter tool and select a cylindrical surface. The diameter of this surface is 14, and the diameter of this hole is 6. Start the Area tool to find the surface area of a selected surface. To measure the length of an edge, start the Length tool and select the edge. The Shift key can be used to select the chain of edges to be measured. Use the Angle tool to measure the angle between two selected surfaces. The Direction collector enables you to define the direction at which the angle is measured. The Distance tool enables you to measure the distance between selected entities. The Projection Direction collector enables you to define the direction or plane that the measurement is taken in. The Measure group of Creo Parametric's Analysis tab provides you with a robust set of commonly used measurement tools that can be used to evaluate your design.
While working in the Flexible Modeling tab, you can find a powerful tool called the Modify Analytic tool in the Transform ribbon group. The Modify Analytic feature provides the ability to change analytic geometry, like cylinders, cones, spheres, and tori. The advantage of using Modify Analytic over Move or Offset is its ability to directly modify the size of the geometry as opposed to the feature's position or offset value. However, we're limited to changing only one surface and one type at a time. If we change the radius value of this cylindrical surface, you can see that the attached surfaces are recreated and kept tangent to the modified surface. Also, the existing rounds are automatically recreated, adapting to the new geometry. Additionally, if we look in the Attachment tab, we can see some interesting options like Create Side Surfaces, Extend and Intersect, and Bounding Edges. Let's have a closer look at these options. By selecting the side edge of the selected surface, we can give it a side surface, or make the front face extend and intersect with the modified surface. If we change the angle of this cone beyond the parts geometry, we can use the Bounding Edges option to indicate where to stop. While working in the Flexible Modeling tab, you can find a powerful tool called the Modify Analytic tool in the Transform ribbon group. The Modify Analytic feature provides the ability to change analytic geometry like cylinders, cones, spheres, and tori. The advantage of using Modify Analytic over Move or Offset is its ability to directly modify the size of the geometry as opposed to the feature's position or offset value. However, we're limited to changing only one surface and one type at a time. If we change the radius value of this cylindrical surface, you can see that the attached surfaces are recreated and kept tangent to the modified surface. Also, the existing rounds are automatically recreated, adapting to the new geometry. Additionally, if we look in the Attachment tab, we can see some interesting options like Create Side Surfaces, Extend and Intersect, and Bounding Edges. Let's have a closer look at these options. By selecting the side edge of the selected surface, we can give it a side surface, or make the front face extend and intersect with the modified surface. If we change the angle of this cone beyond the parts geometry, we can use the Bounding Edges option to indicate where to stop.
Creo Parametric's new 3D Dragger interface has been added to make the process of orienting a component during the assembly process simple, fast, and intuitive. You'll see it as soon as you add a component to the assembly. Of course, you can still reorient a component by pressing the Control and Alt keys while using the mouse buttons to pan and spin within the assembly. And if you don't want to see the new 3D Dragger, you can toggle its display on and off using this icon in the dashboard. But the 3D Dragger is a much faster, more interactive method that in many cases can improve your design efficiency. Each color-coded area of the 3D Dragger is used for a different type of orientation. The shaded arcs of the dragger control rotation about the three axes. The shaded arrows translate the component along these axes. These small, translucent quadrants move the component in the 2D plane. And the small sphere at the center of the dragger is used to move the component in any direction. Sometimes it's faster or even necessary to drag components along selected geometry, and it's easy to do that. Just right-click on the 3D dragger and select Drag Along Geometry from the pop-up menu. Then select the geometry you want to drag along, for example, the edge of this shaft, and now that the edge is selected, the shaft will rotate or translate along that edge. The remaining degrees of freedom can't be used to manipulate the model while dragging along that edge, so they're grayed out. As additional degrees of freedom are reduced by adding more constraints to your assembly, you'll notice that those corresponding portions of the dragger are also grayed out. An example is a shaft inserted in a hole, which limits motion to only one rotational axis and one translational axis, which are the shaft's remaining degrees of freedom. The new 3D dragger provides you with an easier, more interactive method to move your components about in assembly, while respecting the limitations of the constraints you've specified.
Modifying pipeline routing. In this task, we modify existing pipeline segments. Disable all datum display types. In the ribbon, select the Applications tab. Click Piping from the Engineering group. Click Pipe from the Routing group. If necessary, click Display Thick Pipes from the View group to display thick pipelines. Select the pipe segment shown. Edit the line stock. In the ribbon, click Modify Pipeline from the Pipeline group. Select the Line Stock option. Select the pipe segment shown. Click OK. Select Pipe 25A from the Modify Line Stock drop-down menu. Click Apply Changes. Notice that the line stock thickness updates on the pipeline as shown. Edit the bend radius for selected corners. Select the Corner Type option. Zoom in and select the upper corner on the pipeline as shown. Press Ctrl and select the lower corner on the pipeline as shown. Click OK. Edit the bend radius to 40. Click Apply Changes. Notice that the corner geometry updates as shown. Edit the corner type for selected corners. Select Miter Cut from the New Type drop-down menu. Edit the cut number to 3. Edit the cut length to 40. Click Apply Changes. Notice that the corner geometry updates as shown. Edit the flow direction. Select the flow direction option. Select the pipe segment shown. Click OK. Notice that the flow direction is indicated in the model, as shown. Click the Reverse button. Notice that the flow direction updates on the pipeline, as shown. Click Accept Changes. This completes the demonstration.
When you're working in flexible modeling, the Recognize and Select ribbon group provides several shape selection tools to speed up your design process by allowing you to select the surface or surfaces of the geometry you want to change or move. Let's start by taking a look at the Boss and Boss with Secondary tools. They will select simple or more complex boss shapes. But with simple geometry like this, the difference is not that noticeable. However, if we select more complex geometry, you can see the difference when we make a selection using the boss with secondary tool. The cut and cut with secondary tool will select simple or more complex cut shapes as well, but as you can see, if we use the cut with secondary tool, Creo Parametric also includes the pattern of holes on the bottom of the pocket. If you need to select multiple shapes or a combination of boss and cut selections, simply hold down the Control key. When the seed surface of the selection has multiple regions, the surface region selection filter in the lower right can be used to isolate the correct region. After seeing boss and cut with secondary tool, you can pretty easily guess how the round and round with secondary tool will work. They can be used to select round pieces or full sets of round geometry. And just like the previous selection tools, you can hold down the Control key to create multiple round selections. The Recognize and Select ribbon provides you with the shape selections tools that make modeling faster and
Since John has CAD documents checked out in the Recoil 400 workspace, we access that workspace to test our checked out CAD docs view. We do not need to set the Recoil 400 workspace as the active workspace, since we do not plan to create or open any designs. Change to the CAD Documents Only table view. We access this by using the Pick a View drop-down menu. Observe the general status of the CAD documents, and notice that both checked out and non-checked out CAD documents are being displayed. To modify this table view so that only the checked out CAD documents are displayed, first we must access the Customize View List Workspace Listing window, which enables us to manage and create table views. We want to modify the table view so that it displays only checked out CAD documents. In the Set Name step of the New View wizard, we can modify the name for our view. We maintain the selection to display the view in the View list. In the Choose Object Types step window, we select which object types the view manages. We maintain the table view to only display the CAD document object types. In the Set Filters step window, we specify the rules that govern which items are displayed in table rows. The criteria drop-down list is populated with attributes specific to the CAD document types. We filter our view by selecting the general status criterion from the list and adding it to the filter criteria table. Now that the general status criterion is added to the table, we can define an operator and a value. We maintain the selection of equal to for operator. We observe the options available to us for value. Notice there are several status selections. The most appropriate choice is checked out by you. We maintain the displayed columns and the sorting that had previously been established. Therefore, we are finished with our modifications to this table view. Our new view appears in the Customize View List Workspace Listing window, but it is not active. Microsoft Internet Explorer informs us that we need to refresh the Workspace page. Observe that only the checked-out CAD documents appear in the Object List table, that our columns appear in the proper order, and that the objects appear to be sorted first by type, then by number. We change our view back to the default view of All. This completes the exercise.
Draft features are typically used to apply angled surfaces to your design, so that the manufactured part can be pulled from the mold or casting tool it will be created in. Without draft, your manufactured part might get stuck in the tool used to produce it. To apply draft to your model, start the draft tool. Every basic draft feature contains the following 4 items. Draft surfaces. These are the surfaces that the draft angle is applied to. In this example, the draft surfaces will be the cylindrical surfaces of this extrude. A draft hinge. That's the reference that the draft geometry pivots about. Go to the References tab and activate the Draft Hinges collector and select the top of the extrude to be the hinge. Notice that as you move the drag handle, the cylinder stays the same size at the hinge location, as draft geometry is added or removed starting from this reference. A pull direction. That's the direction used to measure the draft angle. You can see in the References tab that by default, the pull direction reference is the same as the draft hinge reference. The yellow arrow in the graphics area displays the pull direction. This is the direction in which your mold or casting tool is pulled away from the finished part. And the draft angle that's applied to your model. It can be as large as plus or minus 30 degrees. If we move to the middle extrusion, we can apply a draft to the 4 side surfaces. Only this time, the draft hinge will be the datum plane running through the center of the extrusion. Notice that the draft angle pivots on both sides of the draft hinge. For our last example, we'll add draft to the 4 side surfaces and use the base of the model as the draft hinge. Notice that the size of the resulting geometry always stays the same at the draft hinge. The draft feature in Creo Parametric is a powerful tool that enables you to create manufacturable, molded designs. When you're working with sheet metal design in Creo Parametric, you can quickly see a preview of your flat pattern by turning on the Flat Pattern Preview from the Graphics toolbar. Notice that the preview window contains its own graphics toolbar. You can toggle the bounding box display to see the overall dimensions of the flat pattern's bounding box. This way, you can quickly monitor the flat pattern size as you progress through your design. Click Flat Pattern Preview again to toggle off its display. A quick look at the model tree confirms that the preview did not create a feature in the part. It's simply a display that can be toggled on and off as necessary. A flat pattern feature unbends your entire part just like an unbend feature does, only the flat pattern feature is always automatically located at the end of the model tree. Start the Flat Pattern tool from the Bends group and your model will automatically be flattened about the default fixed surface highlighted in green. You can select another fixed surface to change the orientation of the flat pattern. Notice that when you create a flange feature, it's automatically inserted before the flat pattern feature. When the new feature is completed, the flat pattern will be resumed. This flat pattern feature behavior enables you to create a flat pattern early in the design process so that you can simultaneously create and detail your sheet metal designs.
Tutorial is for selecting and removing multiple surfaces or gaps for removal. The Removal tool helps you remove geometry without the need to alter feature history or redefine any other number of features. For this demonstration, I want to use the Remove feature to remove parts of these rounds. The first step is to select all the rounds. Now that all the rounds are selected, I want to click on the Editing tab and then click Remove. As of right now, the Remove feature wants to remove every single part of the rounds, but I want to keep these quarter rounds intact. So to do that, I'm going to click Options, and then click in the Exclude Contour box and select the parts of the rounds I want to keep. Now I can press OK, and you'll see that the Remove tool was able to delete the other rounds but keep the other rounds there. I was able to change the feature without being forced to redefine the feature or alter any feature history.
A flat wall is a planar, unbent section of sheet metal. Primary flat walls can take almost any flat shape because they're defined by a sketch. To create a flat wall, click Planar from the Shapes group of the Model tab. Select the Datum Plane top to sketch a wall, then sketch a shape that defines the size and shape of the flat wall. Click OK from the Sketch tab and enter a material thickness for the sheet metal wall. As you can see, it's pretty easy to create a planar sheet metal wall of any shape in Creo Parametric.
Here I have an imported dataset, and I will use it to demonstrate how to replace trimming edges and show how to copy and paste a surface to a new location. First, I'm going to click on Import Data Doctor. Now I'm going to click on this front surface, and now I'm going to click on the Create pull down. Now I'm going to click on the UV Curves pull down and select UV Curve through points. Now I will hold Control and select these 2 points and press OK. Now I'm going to use the curve I just created to replace the boundary edge of this surface. So I will click on the existing boundary curve, select Replace, and now click on the UV curve I just made and click the check mark. Now I'm going to close all the current gaps in my geometry, so I'm going to click on Tools, Find. It's already set to look for gaps, and I'm going to change the value to 1 and press Find Now. Now I'm going to highlight all 5 of these gaps and move them over to be selected and press Close. Now I'm going to click on Import Data Doctor and select Add to Wireframe and then click Repair. Check off Repair Tangency and press OK. Now the last step is to copy this surface and use it to replace this missing surface. So I'm going to highlight the surface, then right click and select Copy. And now I'm going to right click and select Paste Special. And now I'm going to move this surface so that it's closer to where I want it to be. Now I'm going to click on the Placement tab, click on Select Component Item, and I'm going to select this vertice and select this vertice on the assembly. Now I'm going to click New Constraint, and again I'm going to click the corners and set one more edge so that it's fully constrained, and press the check mark to finish the placement. Now I'm going to highlight Surface 271 and Component 247 and click on Combine. Now I'm going to press OK to finish the Import Data Doctor and click OK to import it as a solid.
When working in flexible modeling, and you need to mirror geometry about a reference plane, head to the Transform ribbon group to find the Mirror tool. In this example, we're going to switch on the datum plane display and click in the mirror plane selection box to add the required reference plane. Similar to what you experience with the other flexible modeling tools, surfaces will be automatically extended and rounds will be recreated at the intersecting edges. Additionally, if we look in the Attachment tab, we can see some interesting options. You can control whether the rounds will be automatically recreated and if the mirror geometry will be attached or mirrored as an open quilt. Let's have a closer look at these geometry attachment options. If we unselect the Create Round Geometry checkbox and also unselect the Attach Mirror Geometry checkbox, instead of a rounded solid mirror feature, the result will be a mirrored open quilt of the selected surfaces. The Mirror tool provides you with several options to control how your mirror geometry will be created.
I currently have an incomplete model of an air engine intake, and what I am going to do is create surfaces to blend these parts together. To do this, I'm going to first click on the Style button, then click on Curve. I'm going to click on Free Curve, and I'm going to make 4 free curves between the two features. I'm going to hold down the Shift key when selecting my points so that it snaps to the point I want, and then click down on the scroll wheel to complete the curve. So I'll do this again, and one more time. And click the check mark. Now that my curves are created, I'm going to add constraints to the curve's endpoints to define the shape of the curves. So to do this, I'm going to click on Curve Edit, and I'm going to click an endpoint I want to change the constraint on. And this endpoint, I'm going to now make it normal, and I'm going to make it normal to this plane, so I'm going to click on the plane, and notice that it changed the shape of the curve. I'm going to do this same constraint again on this endpoint. So I'm going to again click normal, and the plane. And notice again it changed the shape of the curve. Now for the rest of these endpoints, I'm just going to change it to be surface tangent. So again, just click on the curve, click on the endpoint, and select surface tangent. Now all my endpoints are completed, so I'm just going to click check. Now I'm going to create my surfaces. So the first surface I'm going to create is between these two curves. So I'm going to highlight them and then click on the surface button. And now I'm also going to highlight these two lines so that the curve is flush with those surfaces. And now press OK. Now my next surface, I'm going to highlight these two curves, then click on the surface tool. And now I'm going to also click on these two curves to set more boundaries for my surface. And that looks good, so I'm just going to click down on the scroll wheel to complete the surface. And now I'm going to highlight these next two curves. Again, click on surface. I'm going to also highlight these lines so that they line up flush, and click OK. Now click OK to finish the surface. And there you see, we created a blend between these two parts.
Assembling using automatic. In this task, we use the automatic option to assemble components. Disable all datum display types. Select Assemble from the Assemble Types drop-down menu in the component group. In the Open dialog box, select component body.prt and click Open. Right-click and select Default Constraint. Middle-click to complete the component. Click Assemble. In the Open dialog box, select component shaft.prt and click Open. Reorient the assembly. Reorient shaft.prt approximately as shown. Notice that the constraint type is set to automatic. Select the surfaces. Notice that the system creates a coincident constraint. Drag the shaft.prt up and out of the hole. Select the two surfaces. In the dashboard, select the Placement tab. Edit the constraint type to distance if necessary. Edit the distance value to 1. Right-click and select New Constraint. Select the two surfaces. In the Placement tab, edit the constraint type to Angle Offset if necessary. Edit the angle value to -35 or 35 as necessary to achieve the position shown. Middle-click to complete the component. Click Assemble. In the Open dialog box, select component cover.prt and click Open. Reorient cover.prt approximately as shown. Again, notice that the constraint type is set to automatic. Select the surfaces. Notice that the system creates a coincident constraint. Right-click and select New Constraint. Select the two surfaces. Notice that the system creates an oriented constraint. Right-click and select New Constraint. Select the two surfaces. Select the Placement tab. Edit the constraint type to coincident if necessary. Middle-click to complete the component. Click Assemble. In the Open dialog box, select component arm.prt and click Open. Reorient arm.prt approximately. Again, notice that the constraint type is set to automatic. Select the surfaces. Notice that the system creates a coincident constraint. Notice that the taper direction of the cones is not aligned. In the dashboard, select the Placement tab. Edit the constraint type to Centered. Enable Plane Display. Right-click and select New Constraint. Select the two planes. Notice that the system creates an angle offset constraint. In the Placement tab, edit the constraint type to coincident. Middle-click to complete the component. This completes the demonstration.
All drawings contain at least one sheet. When additional sheets are created, They're managed using the Sheets tab and dialog boxes. The most common sheet functions can be accessed using the Sheet tab's area, located at the bottom of the interface. Thumbnail previews of each sheet are shown when the cursor passes over the tabs. You can easily navigate through or switch between sheets by clicking on different tabs. To create a new sheet, click New Sheet from the tab area and enter a name for the sheet in the text box at the top of the graphics area. Pressing Enter accepts the default name. Sheets can also be named or renamed by double-clicking their tabs. To copy an existing sheet, right-click on the sheet to be copied, and then select Move or Copy. Then, in the Move or Copy Sheet dialog box, select where the sheet will be inserted and enable Create a Copy. Click OK and then press Enter to accept the default sheet name. The order of sheets can be easily changed simply by dragging their tabs to new positions. To delete a sheet, right-click on the Sheet tab and select Delete from the pop-up menu. Many times there are different formats applied to different sheets in a drawing. To change the format used on a sheet, click Sheet Setup from the document group. You can then select the format that will be used on the current sheet. Creo Parametric enables you to easily create, configure, reorder, and delete sheets in your 2D drawings. All drawings contain at least one sheet. When additional sheets are created, they're managed using the Sheets tab and dialog boxes. The most common sheet functions can be accessed using the Sheet tab's area, located at the bottom of the interface. Thumbnail previews of each sheet are shown when the cursor passes over the tabs. You can easily navigate through or switch between sheets by clicking on different tabs. To create a new sheet, click New Sheet from the tab area and enter a name for the sheet in the text box at the top of the graphics area. Pressing Enter accepts the default name. Sheets can also be named or renamed by double-clicking their tabs. To copy an existing sheet, right-click on the sheet to be copied, and then select Move or Copy. Then, in the Move or Copy Sheet dialog box, select where the sheet will be inserted and enable Create a Copy. Click OK and then press Enter to accept the default sheet name. The order of sheets can be easily changed simply by dragging their tabs to new positions. To delete a sheet, right-click on the Sheet tab and select Delete from the pop-up menu. Many times there are different formats applied to different sheets in a drawing. To change the format used on a sheet, click Sheet Setup from the document group. You can then select the format that will be used on the current sheet. Creo Parametric enables you to easily create, configure, reorder, and delete sheets in your 2D drawings.
This technical tip is to discuss flow-dependent fittings and pipeline parameters in piping design. If we zoom into this pipeline here, you see that I've got a check valve, and the check valve indicates the direction of the flow. If I turn the flow direction on, you can see that the red arrow indicates the direction of the flow. If I reverse the flow direction, you'll see that the flow-dependent fitting, i.e. the check valve, does not currently reverse. To fix this, what we can do is we can select the fitting, select Tools, Parameters, and add a new parameter called flow_constrained. Set this parameter to be an integer and give it a value of 1. When we come back to piping design, reactivate the pipeline, show the flow direction, and now when we flip the flow direction, you'll see that the flow dependent fitting also reverses. Next tip I want to show you is on the pipe parameters. Now for this pipeline here, you'll see that if I select the pipe solid and choose open, under Tools, Parameters, you'll see that the pipe centerline parameters have been added to the pipe solid. So for example, for this pipe here, its currently size is set to be 50A schedule 40. If I change this design, select a reducer for example, and flip the reducer, when I select this pipe solid again and choose open and go to parameters, you'll see that the size has changed from 50A to 100A. So this means every time the pipeline changes, the pipeline solid parameters are automatically updated. This concludes the technical tip on piping design.
Projected toolpath for 4 5-axis cut line. In this task, we review the current toolpath. Disable all datum display types. Right-click 1 Surface Milling OP010 from the model tree and select Edit Definition. Review the toolpath. In the menu manager, click Play Path Screenplay. Click Play from the Play Path dialog box. Click Close from the Play Path dialog box when complete. Note: you can slide the display speed selector right or left to speed up or slow down the display. In this task, we update the parameter Gouge Avoid option to give a projected toolpath. Click Step Parameters from the Update group. In the Edit Parameters of Sequence dialog box, click All and edit the Gouge Avoid option to project tool. Click OK. Click Screenplay from the menu manager. Click Play. Click Close. This completes the demonstration.
A chamfer is a type of feature where an edge or corner is beveled. In Creo Parametric, there are 2 types of chamfers: corner chamfers and edge chamfers. To create an edge chamfer, click on Chamfer in the Engineering tools and select Edge Chamfer. Next, choose multiple edges by selecting the first edge. holding Control and selecting the other edges you want to be chamfered. These 4 edge chamfers are in the same set, meaning that each of these chamfers will have the same dimensions. The default chamfer selected is d times d, which creates a chamfer at the distance from the edge along each surface. To change the distance, move either these white boxes or insert a specific value. Let's create another chamfer. Click New Set to add a new set of chamfers. This time we'll add material rather than remove it by choosing these edges. This set of chamfers will be a D1 by D2 type chamfer, which creates a chamfer at the distance D1 from the selected edge along one surface and a distance D2 from the selected edge along the other surface. Click OK to finish the feature. A corner chamfer removes material from the corner of a part, creating a beveled surface between the 3 original surfaces common to the corner. To create a corner chamfer, click on Chamfer in the Engineering Tools and select Corner Chamfer. Next, select a vertex that will be the reference of the corner chamfer. Similar to the edge chamfer, to set the distance from the corner, either drag this white box or insert a specific value. Click OK to finish the feature.
Auto round. In this task, we utilize an auto round to create rounds on a complex model. Disable all datum display types. From the engineering group, click Auto Round from the Rounds Type drop-down menu. Edit the convex radius value to 1 if necessary. Select Same for the concave radius value if necessary. Select the Scope tab and observe the options. Click Complete Feature. The auto round will take a few moments to generate. Select the auto round from the model tree, right-click and select Edit Definition. Select the Exclude tab. Press Ctrl and select 4 edges to exclude. Click Complete Feature. The auto round will take a few moments to generate. Drag the Insert indicator directly before the auto round feature. Select Sketch 1 from the model tree, then click Extrude from the Shapes group. Edit the depth to 15. Click Complete Feature. Right-click the Insert indicator and click Cancel. Click Yes. Notice the auto round has encompassed the inserted feature. Select Auto Round 1 from the model tree. Right-click and select Convert to Group. Click OK. Expand the local group, Group Local _ Group. Right-click the local group and select Ungroup. Notice that the auto round has been converted to a series of standard round features.
Before I start, I'm going to make sure I don't have any other Creo project windows open. Here I have a basic assembly line with various machinery and objects in the environment. I begin by selecting the Mannequin tab on my ribbon, then clicking the Insert Mannequin button. A dialog box appears. The first reference I select will be where I want my mannequin to stand. This is done by left-clicking in that spot. Here I'm putting my mannequin close to the center of the assembly line floor. The next reference I select will dictate which way my mannequin will face. This is also done by left-clicking. As you can see, the mannequin faces whatever surface I select as my second reference. I'm going to accept the mannequin's current position by clicking OK. If I don't like where my mannequin is standing or facing, I can go back and edit my references by first selecting the mannequin in the model tree, then going up to the Mannequin tab and selecting Edit Placement. Here I'm selecting the reference that I'd like to change, as well as the face that will be the new reference. In the initial dialog box, there are two basic postures I can choose from, standing and sitting. I've already touched on standing, so now I'm going to take a look at the sitting functionality. First, I'm going to import another mannequin into the model tree, but this time I'm going to check the option labeled Sitting in the dialog box. If I select the bottom face of the chair next to the assembly line, the mannequin will now be in a seated position adjacent to the chair. As with the standing mannequin, the next reference I select will be which way I'd like the mannequin to face. Here I will select the wall behind the mannequin. This will result in the mannequin facing that wall. To turn the mannequin around, I'm going to click the flip option to the right of the Select Reference To button. My mannequin should now be in a sitting position on the chair and facing forward. Mannequins are useful tools for assessing the size and scale of an object in Creo. They include more complex functionality than
Creo Parametric provides you with many options to control the display of your models, making them easier to view and work with. When you open a model in Creo Parametric for the first time, you should notice several changes in the display of your model. The first change you may notice is that the display of name tags for all datum features, other than the coordinate system, have been turned off. This cleaner look keeps your model's display less cluttered, making it easier to work with. You can find the name of any feature by moving your cursor over it, and when the feature pre-highlights, its name will be displayed. To turn the display of datum tags back on, go to the View tab, and in the Show Group, you can toggle the display on and off. You should also notice that new lighting has been applied to your models. New solid features will default to this medium gray color that contains lower shine and reflection than previous releases. Creo Parametric includes a new model display type called Shade with Edges. When this display is activated from the Graphics toolbar, all model edges are displayed in black, making the details of your model easier to see and work with. If a solid extrusion is edited to be a surface feature, you'll see that it changes from the gray to a blue-violet color that contains higher shine and reflection. This is true for all surface features in Creo Parametric. To permanently change the display of either datum tags or the model's display type, click File Options, then click on Entity Display. If you change the display settings here and click OK, you'll be prompted to save the setting to a configuration file. If you save these settings, Creo Parametric will apply them the next time it's started. Note that Creo Parametric includes even more graphic enhancements than we've seen here. Feel free to explore.